Okay, so I'm happy to introduce our second speaker for the morning, Anubhav Mukherjee, and he'll be talking about exotic codimensional one manifolds in four manifolds.
Thank you everyone for coming, and thank you for the great invitation. So yeah, let me know if I'm not loud. Also, let me know whoever sitting on the back if you cannot read my handwriting. I'm trying to write bigger scripts. So I'll be talking about one of my recent work about exotic codimension-one submanifolds in four manifolds. So let me start by saying that. Oh, sorry. Okay. So it is one of the key topic of study in four manifold. To understand exotic phenomena. And by exotic phenomena, I meant that those properties which are sort of true in topological category, but not in smooth category. Okay, so in theory or in like the past 40 years, there are mainly three topics of exotic phenomena that has been studied a huge amount, and those are precisely one, exotic smooth structure on four manifold. And this is such as when two manifolds are homeomorphic, but not diffeomorphic. The second one is exotic surfaces. So this is essentially what Princeton proved in 80s, that surfaces sort of determine the topology of simply connected four manifold. And for that purpose, understanding how surfaces sits inside four manifold could give us a better understanding of what is the topology of four manifold. So similarly, we say that a pair of surfaces exotic in a four manifold if they are topologically isotopic, but not smooth. And lastly, the third is exotic diffeomorphism. And this is also of same flavor, that a pair of diffeomorphism that are topologically isotopic, but not. So in today's talk, I'll be trying to introduce sort of a relatively new phenomena in this category, which I'll be calling as exotic embeddings of three manifold. So before defining this notion in a precise way, let me first tell you why at the first place people may find this not an interesting question. So in four manifold, if we start with a pair of exotic four manifold, like we start with X and X prime that are homeomorphic, but not diffeomorphic. What we could do is that in certain sense, we could introduce a new four manifold by connected some another four manifold with X and X prime. And what it does is that it sort of makes them diffeomorphic in certain situations. So by doing connected some other four manifold, we get diffeomorphic copy. So what does that saying that pictorially that we had X and let's say we had X prime, but then I blew another 4 manifold X tilde with both of them, and now they are diffeomorphic. So there is a diffeomorphism going from one to another. In that sense, what we could do is that we could look at this connected free sphere here, and by this diffeomorphism, we could pull back this connected free sphere here. So now notice that these two connected free sphere cannot ever be smoothly isotropic because of some isotropy extension theorem, because we know that if there is isotropy, taking S to S prime, we could extend that isotropy in the whole ambient 4 manifold. But if we do that, that will induce a diffeomorphism between X and S prime, which is not possible as we started with the fact that they are homeomorphic but not diffeomorphic. So there exists an very elementary obstruction of existence of this sort of exotic free manifold, and maybe for that reason people think that this is not interesting. But let me make this problem a little bit more interesting now. So let me define the notion of exotic codimension-one submanifold as follows. Definition. We call a pair of 3 manifold Y1 and Y2 inside X exotic codimension-one if they are topologically isotropic. They are not smoothly isotropic. The third condition is that their complements are diffeomorphic. So now, because of this condition 3, we cannot have that as an example of exotic codimension-one manifold, because clearly the complements are not diffeomorphic. Okay, anyone has any question regarding the definition? So this is the notion for me as what I call exotic codimension-one manifold. All right, so let me say a little bit about what is known here. So recently, by recently, I mean something between 2019 to 2022, there is a series of papers by Burney and Gabay, and independently by Watanabe, where they have proven a great deal of results along this direction. And what they have proved, so they have proved existence of non-trivial free manifold. The reason I call them non-trivial in 4 manifold, and by non-trivial, what I mean is that so they constructed a pair of 3 manifold in 4 manifold that satisfy actually condition 2 and 3. So their example satisfy condition 2 and 3, but they are not able to prove whether those examples are topologically isotropic or not. But condition 1 is still unknown. So I talked to both of them actually, and Watanabe believes that maybe their examples are also exotic in that sense, but David Gabay told me that he believes that their examples are not exotic in that sense. So yeah, so then the question is that how do you construct exotic examples, or how do you see such examples? Okay. Any questions? All right, so before saying any of our results, I would like to propose a few motivational questions that I would be interested in knowing the answer. The few questions I would like to propose. One, that so given a three manifold, why can we construct a four manifold as such that we can find exotic derivatives of y. So this is like more of like a constructive question, because we know for a fact that all three manifolds sits inside some four manifold. And there are many interesting questions regarding those embeddings, like whether those manifolds sits inside string or not, whether it's symplectic or not, and all these sort of questions are very interesting. So we could also then ask that, okay, fine, if I hand you over a three manifold, can you at least construct a four manifold, or we can find exotic embedding for that three? Second question is, what are some simplest examples of manifold exotically embedded in four manifold? So, and by simplest, I mean, we all know that the simplest three manifold is probably a three sphere. So a part of this question essentially asking is that whether can you find different embedding of three spheres, exotic embeddings of a sphere inside four sphere, inside other four manifold. A famous questions along this line is from this conjecture, which is asking whether we can find an exotic embedding three sphere inside four sphere or not. But one could ask a generalization of that question by saying that, okay, can we find any example of an exotic embedded three sphere in some four manifold? So also notice that in four manifold, for example, we know that prime decomposition result is not true. That means we can decompose four manifold in prime pieces. So this question is sort of asking a little stronger version of that, in a sense that is asking that if you decompose a four manifold into exactly same prime pieces, are those pieces are somehow isotopy of each other? And third question I would like to propose. So since we are talking about simplest three manifold, the natural third question will be, what is some simplest four manifold we can find? So does there exist codimension-one exotic three manifold in, let's say, S4, CP2, or S2 process 2? Again, we do not know any, like, I have no clue how to do this, but also this part is very closely related with Snell conjecture. In theory, if we can show existence of codimension-one exotic three manifold in four sphere with maybe some more condition on the mapping class group, one could able to construct an exotic diffeomorphism out of that. So yeah, this part of the question might be interesting, but also super hard. But yeah, I have no clue how to do such. Okay, so any question with or comments regarding any of these questions? All right, so I'll state one result regarding this question two that we are able to prove. So I'm going to state the simplest version of our result, but one could generalize and make a stronger version of it. So this is as follows. That let's say we start with the four manifold as 4 CP2 connected some 22 CP2 bar. And if we decompose X as X1 connected some X2 such that B2 of Xi are equal to 2, then let's consider the connected three sphere here, call it S. Then our result says that then S has infinitely many things of it. So this is saying that if you start with this manifold and you take any decomposition of this, you start with this four manifold and you take any decomposition of these four manifolds in this following way, that is for the case that we equal to, for example, I could take X1 equal to 2 copies of CP2 and X2 equal to whatever is left out. If we do so, and if we now consider this connected three sphere here, then that three sphere actually having infinitely many exotic velocity inside the whole manifold. So I'll not actually prove this result here, but this is sort of application of a family version of adjunction inequality. So we'll be able to produce S1 family of adjunction inequality, and using that adjunction inequality, we are able to prove that such connected some decomposition with this condition should vanish. And it should pass. Oh, yes. So BQ classical. Any question? So far, this is the simplest closed four manifold example that we know where we can find exotic embedding of this sphere. So I'm also very curious if one can find a smaller example than this where we could find exotic embedding of this sphere. The big problem we have in hand is that we need this extra condition of P2 classical between both the pieces to do the gauge theory. It's sort of like similar of like in general gauge theory that we need the condition that B2 classical to 1, we try to decompose it to 4 manifold. And since it's one parameter, we have this extra class 1 and it becomes B2 classical. So yeah, so we are really curious to know if someone has another idea to produce better and smaller examples where we could find exotic embeddings of this sphere. So now I think we are almost to do our latest result, but I can ask another question. Is it any example like we have the analogous problem? Like you have exotic surface, don't you? Don't you get sort of automatically exotic Yes, you could, but then we need to be very careful. So we enjoy that is true, but also do not know any good example of exotic surfaces in complementary. Most of the exotic surface in theory, how we detect it, somehow we build the exotic surface. So essentially, it's equally study the complement. And like for and all these things actually take the complement. So the relative examples. Yeah. So that's true, but then I do not know how to produce, like how to build those things inside a flow. Because the gap of, I mean, you probably know. Any other question or comment? Okay. All right. So now I would like to mention another interesting four-dimensional phenomenon before stating the main result. So this is sort of a very old classic observation regarding the exotic four-dimensional manifold. So it's probably known as Wahl's principle. So while Wahl was studying the H codimension theorem in 1960s, he realized that if you start with a pair of simply connected, exotic four manifold X and X prime, then essentially an application of the codimension theorem says that after connected summing with bunch of copies of this process, they actually become bigger. So in other words, this observation can be generalized in other exotic phenomena, and it's saying that in four dimensions, exotic phenomena they exist, but they are also very unstable, that they do not survive forever. They just they are at certain stage. And this operation is the exponential stabilization. This also now want to understand whether that kind of things happen in codimension-one situation or not, and the answer is sort of yes. In this situation, that whatever example we are able to produce here, in these three spheres, we can prove that after attaching bunch of H2 cross H2 with the four manifold that we constructed here, all these examples actually becomes smoothly. So pictorially, we have this notion that, let's say we have our X here, and we had bunch of like three spheres sitting here, which are sort of exotic in the sense that they are not moving exotic, but once we some of this process, they will be very different. Okay. Now, in this figure, you could see that is everything is simply connected, and these are codimension-one. This sort of three manifolds separate this four manifold. So you could ask in this category that it is enough that we stabilize in one side. For example, in this example, we could see that yes, like one sided stabilization is enough that if you attach connected manifold with this four manifold that is connected with, this becomes everything becomes sort of surprisingly, this is not true, and so here is the main result that now I would like to discuss. So yes, no, so yes for this example. So yes for this particular. You know how to use Python. But did you say how many Python? Oh, so this is I do not know. So there is we also use some more phenomena which is later proven by the Queen and Heron, and you really do not know what to really remember about that. We know some finite number could work. bound. I do not know any bound. Like I know some finite bound, but I do not know really.
In the general case, is it unknown that you can find? Okay. In the general case, is it unknown that you can find and so that it becomes good guys?
So in general case, no, sorry, I'll state the result. So the general case, the unknown case is that if we stabilize both sides, then whether it becomes two sides or not, that is happening. But I state a result which says that one side is stabilized. So that means if this is the picture I have, then they still remain.
But like, it is also unknown that if you have a stabilization on both sides, it might.
Yeah, it's also unknown. So that, yeah, and I have no clue how to do that problem. So. Any more questions? Okay, so now I could state the main result. So there will be a few technical terms in this result, but you can absolutely ignore because the proof I'll give, I'll not mostly assume any of those technical terms. But this is for just being more rigorous. I would mention a few technical terms here. So let K be a knot. In S3 with tau invariant non-zero. And also let's assume that mapping class group of the three manifold Y, which is we can get from sine tau over n surgery on the knot K is trivial. So for example, if we take some kind of hyperbolic knot which has no symmetry in the complement, then we can prove that the mapping class group of such surgery become trivial because there is no room of doing any isometry. So in this situation, so now depending on this n, whether it's even or odd, we can have xn equal to S2 copies of S2 cross S2. And if for n even, and 3 copies of CP2 connected some CP2 buck for n odd, then an xn contains exotic copies of buck. Moreover, they remain exotic in xn connected some m, where m could be any connected four manifold. So no matter what connected four manifold you glue away from the 2 copies of Y, they still remain exotic. So coming back to this picture, essentially saying that this picture is not right, at least for the case of codimension-one. So, but the important fact is that M, for our case, M is a connected four manifold. So that means that we could take a disconnected four manifold, and then we do not know if we glue them like that, whether then the 3 manifold that we constructed to be exotic become smoothly isolated. Anyone has any comment or question regarding the statement? Okay, so last 20 minutes or so, I kind of like try to give a sketch of the proof, how it should go. I try to skip most of the details here, but if anyone interested, feel free to ask me questions after the talk and I'll be happy to explain, but I'll just try to give an example and try to show how things could work. Yeah, so I'll exactly try to give the example that we thought at the first place that help us to write this paper. Maybe knowing this example, maybe we can write. Idea of the tool. So we start with the three manifold, let's say. So with our loss of generality, let's assume two facts that K is positive and N is even. If tau of K is negative, we can always change all the orientation and work with that. And if N is odd, we could just like you can see why the even or odd part comes. So that gives you this or this manifold. So for our case, Y is now 1 over N surgery on the node K. And there is a nice three-dimensional picture as follows, that you have this node K and you do 1 over this. So now we know from Kirby calculus that any of these picture can be converted into a four-dimensional picture. To be more precise, there exists a four manifold. Let's call it Wn, or W1 over N is the boundary of W is 1. And the picture is sort of simple. You could just modify this picture by attaching a meridian here, and now the surgery is minus N and C. So this is sort of the four-dimensional picture of W1 or Wn, whatever you can say, and this has the same boundary Y as P. So also notice that, so as Nino was explaining before my talk, that this is also a kind of two-handle body in that sense that you can construct this four manifold by starting with the four ball and then attaching two handle with one framing 0 along the node K and another framing minus N along the. For that reason, this is a simply connected four manifold with boundary 1. And the boundary is more precisely integer homology sphere because we are doing this particular one. So now in this situation, we have a very interesting or helpful result in hand, which is taken by Friedman. That says that topology of a simply connected four manifold with boundary integer homology P square determined by the intersection form. And this is why now N is even comes to the picture. Since N is even, by some application of Kirby calculus, we could prove that the intersection form of W looks like 0, 1, 1. Now, once we have this particular intersection form, we can actually say more. So this is again by Friedman. This is another very famous result of Friedman, which says that every integer homology sphere bound are constructible format. So this particular four manifold may not be smoothable, but nonetheless, we know that there exists a constructible four manifold. And now, because the tau k is strictly positive, actually we know that for this particular y, the constructible for manifold W naught, so for y, whatever W naught constructible can construct, then it's actually not suitable. That is suitable. Then there is the de-independent manage for this condition kind of code. So we have now a constructible for manifold W naught with boundary y. So now we can actually construct another four manifold with the same intersection form and same boundary y, which is as take W naught and then connect it some S2. And by Friedman's result, now we know that that particular manifold is homeomorphic with whatever manifold W1 were in here we have constructed here, because they have the same boundary, same intersection form. But the only difference is that this manifold is not new. But that's fine. Now we can actually use the fact that this is not stable. So now on H2 cross H2, we have a nice interesting homeomorphism exists, which is coming from complex conjugation. So I so, and now I can extend this map equivalently on the whole manifold W naught connected process because this map has some point by to this connected sum on both H point and extend this map. In other words, I have a homeomorphism H from W naught connected summation of H2 itself. And now let's study this homeomorphism. So this homeomorphism is something interesting in a sense that this homeomorphism, first of all, restricted on the boundary identity, because the way I extend over W naught is by identity, and Y is boundary of W naught. So that is one. And the second situation is that this particular homology is sort of changing the orientation quantum. The orientation of the sort of the H plus quantum. In other words, the restriction on H plus is minus I. So I have this homeomorphism here, and now I could pull back this homeomorphism on W1. So now I can pull back. This will be fun. So without lots of guarantee, let's also call this homeomorphism A. So now I have a homeomorphism on W1 over N with the same exact condition that is the identity, and you've got the homology on the H plus. Now we could actually use a fact which is generalization of Donaldson theorem here. So
French is not together. On the ball.
yeah. And you can do a slight isotopy, like
But the French is not together.
but it's the boundary to be a state. So even if it's not people like put some more isotope.
But that on that street.
Yeah, I can use that. That's a great point. You need to stop. Okay. So now we are in this situation, and then we have an homeomorphism which is sort of active in the homology. So now we could actually use a fact which is sort of generalization of Donaldson theorem So I'm not giving the explicit statement here, I'm giving a shortcut here, but we could actually make it more generalized result for new all the new known things like alpha, beta, gamma, and so on. So a generalization of is that if the partial invariant of the boundary is less than equal to 0, then a map which is identity on the boundary and reversing the homology of the Princeton bundle cannot be smooth. Plus that it cannot be smoothable. And now here to conclude delta y is less than equal to 0, we can use the tau invariant, because if tau is positive, that implies that the invariant of 1 over n surgery of A is negative, and this is nothing but 2 times partial. So this fact then implies that the partial invariant is less than equal to 0. So this particular homeomorphism that we have now constructed is not. Okay, so now that we have this homeomorphism in hand, our goal is to construct exotic embedding of a 3 manifold. So we'll do as follows. So now we have this picture that we have W1 over n, and over here we have a homeomorphism H, which is not smoothable. So one thing we could do is that we can now take a double, like take another copy of W1 over n and do upside down and glue on top of that. And I could extend, so let's call it minus, and I could extend this map by minus H, because notice that restriction on the boundary identity, I could just move them back. So I have now a well-defined homeomorphism here. So now the question is that what is this new 4 manifold? So here is again come back to this picture. So that was W1 over n. And the way doubling construction works for 2 handle bodies is that, so this is in classic way we call doubling construction. We just attach 0 frame meridian to each of the 2 handle of the original formula. So if you do so and do some Kirby calculus, you could see that this picture now is same as this picture, which is nothing but 2 copies of S2 cross S2. So this picture is just connected sum of 2 copies of S2 cross S2. So my claim is that this particular Y has an exotic copy now in this format. Now to see how we can construct, we're again going to use this new homeomorphism H tilde star. So there is another result now by Wall we could use here. So Wall proved that any automorphism of the intersection form of the homology of the intersection form of H2 cross H2 can be realized by diffeomorphism. So that means that there is another diffeomorphism F in connected sum of 2 H2 cross S2 diffeomorphism such that the action on the homology is That's called H tilde. It's same as this map, H tilde. And now we know that by Friedman, that if you have a simply connected four manifold and you have two maps or two homeomorphisms that induce the same action on homology, then they are topologically isotropic. So Friedman's implies that F is topologically isotropic to H tilde. Okay. So then we can see another copy of Y as F of Y. So my claim is that these two three manifolds are now exotic. So claim for F of Y are exotic. So it's obvious that they are topologically isotopic because Y is sort of fixed point of H tilde, and then there is a topological isotopy that taking F to H tilde. So in other words, we could use that topological isotopy to move Y to F of Y. So by this observation, Y is topologically isotropic to Y tilde. Sorry, F of Y. Also notice that their complements are diffeomorphic because we constructed an explicit diffeomorphism F. So that helps us to determine that the complements are diffeomorphic. So condition 3 also satisfied. Now notice that, so what happens if now they are smoothly isotopic? So if these two things are smoothly isotopic, then I can further isotope F such that that doesn't change the action on the homology, right? So if I further isotope F, then I could find F restricted on Y is identity. But if that is true, then that implies that I would have a diffeomorphism on Wn whose homology action is exactly this, because then homologically F and H tilde are same. So if I can further isotope F so that it is now identity on H, then that will induce exactly the same homological action on one of the phase W1 over K. But that will contradict the homology equation, and the homology equation says that this cannot be realized. So because of this observation, we are not. And now to finish this proof, notice that we can completely carry out all this construction even if we connected some four manifold in one of the two sides. The advantage is that we have H on both the sides. So no matter which side we attach a connected four manifold, we could just look at the other side of the picture and do the same analysis and conclude that these two remains exotic even after you connected some any connected four manifold. But of course, you notice now that if we connected some both the sides, then we cannot no longer carry out this argument. So to finish my talk, I would like to propose this, that at this point, we do not know any example of exotic embeddings of three manifolds which remain exotic after you connected some or after you stabilize both the sides. So I'd be really curious to know if anyone has any idea how to construct such example. This is a good point to stop, and I'm happy to answer anyone who has any questions.